In this video, we're going to talk about cubic functions. Now, for a cubic function, it's very similar to a quadratic function. So we have, instead, the largest exponent is a 3. So we could have an x cubed term, an x squared term, an x term, or a number term. So that means there's 1, 2, 3, 4 possible coefficients in front of all of these values. The typical cubic looks something like you see on the graph here. And our parent function is going to be x cubed, and x cubed, this is a function that crosses the origins. The x and y are both 0, 0, and it is a function that looks something like this. So we see that for a cubic we have kind of like a quadratic, but instead of being symmetrical, the other part is kind of going up. And that's one way that we can see a cubic. There's always going to be one part going towards a negative infinity, and the other part is going towards positive infinity. In this video, we're going to go through two main examples that the IB are using for cubic functions. And they're paper 2 style questions, so very involved questions. Question 1. A maximum theoretical power that can generate by a wind turbine can be modeled by the following function, where P is power in watts, A represents the area swept by the turbine blades, D represents the air density, and V represents the wind speed. A certain wind turbine has a swept area of 80 meters squared, and it is located at sea level where the air density is this number here. Find the cubic model for this turbine. So in this question here, we're given what the swept area is. Swept area, that corresponds to the value of A. So we know A has to be equal to 80, and the units match. And then air density, that is our D value. So we know that D is going to be equal to 1.225, and the units match as well, what we have here. Perfect. So I can replace that into my function. So my function is now going to be P is equal to 0.297 times A, which is 80, and times D, which is 1.225. The V, our wind speed, is going to be our variable that we're interested in. In your calculator, you can go ahead and simplify this. And we should get that P is equal to 29.106 times our volume cubed. So this is going to be the equation we're going to be using to solve all of our questions. Part C. Use your model to calculate the maximum theoretical power generated at the wind turbine when the speed is 10 meters per second. So for this question, speed, what does speed represent? Speed is the value of V. So this question is basically telling us what our V is, and we're looking for power, which is P. So I can solve this question by having power is equal to 29.106 times our speed, which is 10 cubed. And we get that the power for the 10 meters per second speed is 29,106, and the units for this for P is in watts. Part C. Given that the wind speed above 20 meters per second are strong enough to cause damage, determine if the wind turbine could produce 3,000 watts. So for this question, we need to compare what happens when we have a speed of 20 meters per second, and if that is above the watts that is produced. So first, let's calculate what is the watts produced, the power, when we have a speed of 20. So I'm going to write this down here. The power when we have a speed of 20, we can use our formula to calculate this, 20 cubed. When you put this into your calculator, we should be getting 232,848 watts. Now let's look at what the question asks. Given that the wind speed above 20 meters per second are strong enough to cause damage, can the turbine produce 300,000 of watts? Well, the answer to that would be no, because when it is at a speed of 20 meters per second, it is not producing 300,000 watts. So no is our answer cannot produce 300,000 watts. And part D, determine a reasonable domain for our model. So the reasonable domain for our model, this is talking about our x-coordinate, and our x-coordinate is our speed, our v. So since v is talking about speed, well, we can't have a negative speed. So we know that our speed is going to have to be bigger than or equal to 0. And then we are told that given that the wind speed above 20 meters per second are strong enough to cause the damage, well, we're never going to want to have a wind speed bigger than 20. So we're going to have 20 be our maximum. And I'm going to include 20 here because it says anything above 20 is strong enough to cause, but it doesn't say that at 20 it's strong enough to cause damage. So this is going to be a reasonable domain to ensure that we don't have a damaged wind turbine. The next example is a very typical cubic example for the IB. It reads, the dimension of paper A4 to the nearest centimeters are 21 by 30 centimeters. It is possible to create an open box by cutting out square corners and folding the remaining flats up as shown in this diagram. So we see that we have our A4 paper, we're removing the 4 corners, and then we're folding these flaps up so that it creates a box. Develop a cubic model for the volume of the open box that can be created using this model. So this question is a little bit more challenging than the first one because we need to create this model. We need to create this model that talks about volume. Well, this volume of the box we know is going to be our length times our width times the height of the box. So the volume is going to be length times width times height. Now, in order to create a model, we're going to need to always use one variable. So we're going to have the volume equals, and everything needs to be expressed as one variable. Notice that in this question, they're already introducing a variable to us. They're introducing this variable, x. So each of these squares that are removed are of size x by x. Let's talk about what is left. So we know that this piece of paper is 21 by 30 centimeters long. So that means the longest side is 30 and the shortest side is 21. Okay. Well, if we go from our first image to our second image, and we think about what is the length of just this part here. So just this part here, well, that's the full 21, and I'm subtracting x from one side and subtracting another x from the other side. So the length of this is going to be 21 minus 2x. And if we think about the length of this side here, well, what is the length of this one? Well, this time it's 30, but I'm subtracting x and subtracting x to the other side. So I'm going to have 30 minus 2x. That's going to be talking about the base of our box. So this rectangle corresponds to the base of our box. So now we're able to represent our width and our length using x. So our width is actually 30 minus 2x, and our length is 21 minus 2x. And now we just need to represent the height. What is the height of this prism? Well, the height is folding up these flaps upwards. And what's the measurement of these flaps? Well, one side is going to be our 30 minus 2x. But all of them have the same width. All of them have x removed. So that means that the height of my prism is going to be x. So now I'm in a good position to write down what the volume of my shape is. I'm going to write it at the bottom so I have more space. So the volume is going to be 21 minus 2x times 30 minus 2x times x itself. I can expand this, and if I expand this, I can make sure that I FOIL, right? So I'm distributing, multiplying each term. And when you simplify this out, you get 630 minus 60x minus 42x plus 4x, and all that is multiplied by x. And then we can simplify this further by combining our like terms. So these two are like terms. When I combine them together, I get 630 minus 102x plus 4x squared, x squared. And all this is times x. And then my last step is to distribute the x to all of these terms. So we have 630x minus 102x squared plus 4x cubed. And now this is the model that we're going to be using to talk about the volume of our shape. So this is part A. Part B, determine a reasonable domain for your model. Domain means we need to talk about our x coordinate. So our x coordinate, this refers back to the little piece that we're removing, right? So this x that we're removing, well, since it's a length, we need to have our x be bigger than 0. And what happens if x is equal to 0? Well, if x is equal to 0, that means that we're not going to have a height to our prism. So we wouldn't even have a shape in the first place. So we don't want x to be equal to 0, just a little bit bigger than 0. And let's talk about the other restriction to x. X can't be an infinite amount because we're removing it from a fixed piece of paper. So if you're removing it from a fixed piece of paper, we need to create another restriction. Let's think about what happens when you remove these x's to the side 21. So if you're removing your x by the side 21, we're creating this side which is 21 minus 2x. Well, in order to have a shape, 21 minus 2x, this needs to be bigger than 0. Right? So in order to be able to have a shape, we have to have a side length. So when is this going to be bigger than 0? Well, we can solve this out. We can add 2x on both sides. We can divide by 2. And we're going to get 10.5 is bigger than x. So this is the second restriction to my domain. X cannot be bigger than 10.5 because if it's bigger than 10.5, we are not going to have a length to our shape. Part C, find the dimension of the open box with the largest volume. So the largest volume that can be created using this model. Largest volume means we're looking for the maximum point. Okay, so I have a function. Let's put this into our calculators. So in your calculator, take some time right now and insert your equation. Then we can click on graph. And we'll notice that the graph is definitely not what we want, right? We're only seeing part of our function. So we're going to zoom out and see what is happening here. So if I zoom out, oh, I'm starting to see that there seems to be 1, 2, 3 lines, which is good. That's what we want for cubics. Now, the domain seems reasonable, but my y is definitely not big enough. So I'm going to go into my window and I'm going to change my y maximum. 40 is definitely not big enough. Notice how we have some very big numbers here, right? 630. So I'm going to try and put 1000 to see what's happening here. And I graph it. Okay, the function looks better, but I'm still not seeing, since it's a cubic, I want to be able to see these 2 points here. So I'm going to update my window so that my y minimum will be increased, let's say to 200, and my y maximum, let's make that even bigger. Okay, that's better, right? And we can clearly see with this graph that we have a maximum point. So we're looking for this maximum point up here. So second function trace, maximum point. They're going to ask me to go to the left of the maximum, to the right of the maximum, and then guess the maximum point. And we're going to get that the maximum point happens when x is equal to 4.05. So 4.05, if I rounded 4.06, and the maximum is 1,144. So find the dimensions of the box. The dimensions, that means our length, width, and height. Well, if the maximum happens when x is equal to 4.06, well, that means that my height is 4.06. My length was 21 minus 2x, so 21 minus 2 times 4.06. And the width was 30 minus 2x, so 4.06. You can do these calculations, and you're going to get a length of 12.9 and a width of 21.9. So these are the dimensions that we're going to have when we have a maximum. And the last part of this question is part D. So calculate the maximum volume of the box. The maximum volume of the box, then we have that already in the maximum point. So for part D, the maximum volume is going to be 1,144. And for units, we are in centimeters cubed.